Hi, everybody. The purpose of this video is to introduce you to the theory behind the X-ray diffraction measurement that we're going to do, okay? The theory is laid out in the handout as well, but I thought this video might be helpful too. Here, hold on for a second, and we're going to go through this in a PowerPoint. Okay, so we're going to do a lab on X-ray diffraction, and we're going to use it to find the crystal structure and the atomic spacing of several different materials. And in doing so, you're going to end up figuring out the size of the atoms in the crystal. Okay? At least the crystals we're going to look at will all be alkali halides, and you're going to find the size of the halide atoms, the different positively charged ions in the crystals. Now, X-ray diffraction is a perfect tool for this because, as we found, atoms in a crystal act like a diffraction grating for X-rays. And by using X-ray diffraction, we can determine crystal structure and lattice constants. Materials crystallize in a number of different forms. There are actually 14 different distinct forms that three-dimensional materials can crystallize into. Seems like a lot, but what's interesting is that these are the only 14 types. In any event, although you're going to determine the crystal structure of your samples, we're going to make it easy for you, and we're going to tell you that the materials are cubic. They're one of the cubic types. So we only have to focus on these. Here are three cubic types. Simple cubic, where the atoms are just on the corners of the cube in each unit cell. Body-centered cubic, where there's an additional atom at the center, and face-centered cubic, where there are additional atoms at the faces of the cube, much like the number 1 mark on a dice might be, okay? So atoms at the corners and an additional atom at the center of the face, okay? So the crystals we're going to look at will be one of these types. We're going to analyze our data with an X-ray diffractometer like this, okay? So as we discussed in class, in this apparatus, there's an X-ray source, which produces a beam of monochromatic X-rays. They hit our sample, which will be mounted here, and then there's a detector. And the detector, of course, detects X-rays if there are X-rays scattered at this angle. When the experiment runs, the sample stays constant, doesn't move, and the X-ray source and the X-ray detector both move up. And we sweep out this angle, theta. And as we sweep out the angle, we look for diffracted X-rays. And what we expect is that we'll find diffracted X-rays anytime we satisfy Bragg's law, which is written here. N lambda equals 2d sine theta. And in this formula, remember, n is an integer, lambda is the wavelength of the X-rays, which is known, and theta is the angle measured from the plane, and finally d is the interplane spacing. So if we do this experiment and we measure an angle, we can use it to determine d, the interplane spacing. Sounds great, right? Only it's a little more complicated than this. If we imagine our crystal, there are actually many types of crystal planes, all with different spacings. This is the one we looked at before, but here is another way to draw the planes of atoms, and here's yet another way. Which of these give rise to Bragg scattering? Okay, and how can we keep track? Well, the fact is that they all give rise to Bragg scattering, but at different angles, and we need a scheme to keep track of them all, because they're going to be, in principle, so many different types of plane spacings, and so many diffracted lines. So we keep track of these through something called the Miller index system. And for us, the Miller index is relatively straightforward. It's just this. We can draw these planes of atoms. Here are 3 different possibilities among all the possibilities that exist. And we can identify a plane of atoms by drawing a vector that's perpendicular to the planes. So for each plane, the vector is unique, right? Then the Miller index gives the components of that vector. So for example, here, in case A, the vector points in the xy direction. So the components of this vector are 1, 1, 0. Okay? Component in the x direction, component in the y direction, no component in the z direction. Of course, this is a two-dimensional drawing. In case B, the Miller index is 0, 1, 0 because the vector just points in the y direction. And in case C, a little more complicated, you can show that the vector is 1, 2, 0. So the Miller index for this plane is 1, 2, 0. Okay? Now, for different cubic types, for different crystal types, we can relate the plane spacings to the distance between the atoms. But in cubic crystals, it's particularly simple. Here's the rule. For cubic crystals, the interplane distance, so the interplane distance d for planes with Miller index h, j, k, is just given by A, that's the lattice spacing, divided by square root of h squared plus j squared plus k squared. So for example, for this case, where the Miller index is 0, 1, 0, it's easy to show that the plane spacing that we observe will just be the lattice constant, A. So the plane spacing is just the same as the distance between identical atoms. But for the case 1, 1, 0, it'll be different, right? Because here, the plane spacing is clearly smaller than it is in that case. In fact, what our rule says is that the plane spacing is going to be A divided by the square root of 1 squared plus 1 squared plus 0 squared, or A over root 2. And for the third case, it's quite similar. Now the plane spacing will be A over square root of 5. And you can see that it's clearly shorter than the other two, just as this formula says. Okay? So there are many different planes. There are many different ways to draw planes in a crystal. We get Bragg scattering anytime any set of planes satisfies the Bragg scattering law. And when we see the scattering, we can determine the interplane distance. And then if we know the Miller index, we can relate that to the lattice constant. Okay? So this is going to give us a protocol for doing our measurements. So here's how it's going to work. First, we're going to do the X-ray measurement and get our X-ray data. This is what it might look like. This shows peaks at various angles. Oh, one detail. On our machine, when it makes this graph, it's going to show X-ray counts, that's intensity, versus angle. But on the angle axis, it's actually 2 theta, not theta. I don't know why they do this, but it's kind of traditional. So something to be aware of. Anyway, let's leave that aside for a moment. Very good. So we'll get this pattern of lines. Now, we can use this pattern of lines to do a couple of things. And one thing we can do is figure out the structure, okay? So, for example, if we were looking at a simple cubic structure, then every time we had a set of planes with a different Miller index, we would expect to see diffraction from that Miller index. And so we should get a pattern of lines that looks like this. We don't need to know anything more about the material than that it's simple cubic to know that the pattern of lines should look like this, okay? On the other hand, if it's face-centered cubic, well, it's still a cubic type. So we're still dealing with the same lines, but for face-centered cubic, there's an additional selection rule. And that's that we only see lines where H, K, and L are either all odd or all even. If you want to know where that selection rule comes from, you're going to have to dig into the theory of X-ray scattering a little bit further than we're going to in our course. But this is the selection rule for a face-centered cubic structure. For body-centered cubic, again, it's the same set of lines, but now the selection rule is different. Here we only see lines where h plus k plus l adds up to an even number. So these give us distinct patterns. Now, if you compare the pattern of lines that we see to these three different patterns, you'll be able to see pretty quickly which structure this material must have. Okay? So think about it. Have you figured it out? Okay. Clearly, it's face-centered cubic because this one has these two lines, as we see here, and then a gap, and then two more lines, as seen here. And it's the only pattern that matches. So now that we know what the pattern is, we know what the Miller indices are for each of the lines. That was the important thing that we needed to find. And once we know the Miller indices, we know everything. So now the next step in this process is to use the measured diffraction angles and Bragg's law to find the interplane distances. So in this set of data here, here are the angles that we measure. So here are the angles that we actually measure: 38.24 degrees, 44.51 degrees, and so on. But these are 2 theta. So we have to divide by 2 to find theta. Oh, and theta here is also in radians, just because Excel likes radians. Anyway, here's the angle theta. From that, using Bragg's law and using the wavelength of the X-rays, which is known, we can find the interplane spacings, okay? And then if we know the Miller index, we can use the formula I showed you a minute ago to figure out what the lattice spacing must be, okay? So for this particular line, which has theta of 0.333707 radians, the interplane spacing was 2.3517 angstroms. And because this is a 111 line, we have to multiply this by the square root of 3 to find the value for A, and we get 4.073 angstroms. Okay, and then we can do this for the next line and the next line and the next line. And if we've done this all right, then all these values of A should be equal to within error, okay? And you can see that all these values are all very close to each other. If you've made a mistake with your assignments or with your structure, then you'll be able to tell because these values won't be equal to each other, okay? It's like a flat. And then finally, we can take the average of all of them, and that's our lattice constant. All right? So it's straightforward enough, but this is the technique you're going to use on all the materials that you measure in the X-ray lab, okay? And in the end, you'll have the lattice constants, and that's what you need to make the final graph. All right, I'm going to stop here, all right? 1 second.